Okay, so picking up kind of where we left off last time, I'm going to do a super duper quick review of the big ideas of what we started developing last time. It's the idea of a vector surface integral. We revisited the idea of flux. Recall all of this from chapter 3, right? So if you want to know how to compute flux, but specifically how flux would be computed over a curved surface with a non-constant vector field. Right? Chapter 3 doesn't address this at all. So if you'd like to do that computation, the idea is to chop everything up into little pieces. That's kind of what we do, right? We chop everything up into little bitty pieces, on each of which the computation is old news. Basically a flat piece of surface with basically a constant vector field, right? Again, the classic move, every integral we've ever computed, you chop up your domain into little pieces on which whatever question you're interested in is relatively easy, and then you add up over all those pieces, right? So it turns into an easy question on these pieces, and then we add up over all the pieces like so, and that gives us this new expression called a vector surface integral that I prefer to write like this. I just think it's kind of the most elegant, really. It's certainly the most compact, right, of our notational options. I like the fact that the ds vector tells you everything about what you need to know about the little piece of the domain that you're looking at. Right? It's not like half in the differential and half in the integrand. That's kind of messy, really, if you think about it. The ds vector is everything you want to know about that little piece of the domain. The only other things you need to know are the vector field, which everything about the vector field is, not necessarily related to the surface. It's independent of the surface. So that's my preferred general notation. And then we talked about how to compute these things, right? Because everything that you need to compute this, and again, I like that notation better, but it's easier to do this particular development starting from here. Everything you need is stuff we already know. And you plug that all in, and you end up with this computational formula. This computational formula right there. Nice, easy way to compute flux over a surface of a vector field. Everything here can be computed in terms of the parameterization. Okay, and then we ended last time with a casual example, right? Now, reminder, I did commit a math crime here, right? And I said we'll come back and address that later. Beforehand, we got one in the win column. We computed the flux of this specific vector field through this specific surface by just using this formula, right? And of course, in order to do so, I needed to compute the capital N. All right, so you got to parameterize your surface and take the partials and take the cross product, right? There's this whole deal here to get your capital N vector. Missed. I should do that more slowly. Capital N vector, which goes there, and then it's just a matter of plugging in. Okay. All right. So we then, I believe, spent a bit of time talking about the question of the parameterization, and does the parameterization matter? And it turns out that it does, because the problem comes to us. The problem comes to us with I should make a better color choice. Let me do the dark green. A problem comes to us with a surface that is oriented one way or the other. We don't know which way, generally speaking. It's not always upward, always downward, always to the left, always to the right, always inward, always outward. No, there's no convention. A surface can be oriented either of two directions. And it's kind of arbitrary which one you call positive. So that being the case, when you parameterize, you are making an arbitrary choice that will determine your capital N vector, which therefore determines what I like to call your parametrized unit normal, and it's a dice roll, a coin flip as to whether the one that you arbitrarily picked will be the same as the one that was given in the statement of the question. It's a coin flip. Right? You got to be heads up about that. And this is the little math crime that I committed in the development on the previous page. Right? What I did here is I assumed, inappropriately, that the normal vector that comes in the statement of the question, the normal vector that's intrinsic to the surface, the normal vector that's pointing in the direction of your ds vector, I just assumed that that would be in the same direction. Let me come down here where this is fleshed out more. That I assumed that the orientation that came with the question would be the same as the orientation that would result from my pulled out of thin air parameterization. And you can't assume that, right? That's the coin flip. There's a half a chance that I got this wrong. So, that's a worry, and we're going to have to be careful about that. So I'm going to write, when I write down the relationship between the ds vector and the parameterization normal capital N, you'll notice in here that I'm including, very importantly, I wanted to switch the colors. Very importantly, a plus or minus question mark. Because you cannot assume that your parameterization orientation and your intrinsic given orientation will be the same. You just can't assume that. Always heads up. You always have to check. That's the nature of the beast. Okay. All right. Now, good news. Other than that, as long as you've got the right orientation, the parameterization doesn't matter. So orientation is the only thing to be worried about. Any other aspects of the parameterization, it's fine. Don't sweat it. Yeah.
Would you recommend, instead of using the f big N equation, using the f dot product normal vector times the magnitude of the big N?
Well, so we've got these various different formulas here for flux. Oh gosh, let me just try to find that. This is I'm trying to find a black colored button on a black colored pen, and it's really hard to do in the dark. Okay, so flux. You can think of it in the most compact notation. You can think of it from this sort of unit vector apparent notation, or you can use the parameterized notation. But you just have to be aware of the differences. When you're just writing about these things in general, and you're not trying to actually compute, the compact notation's great, right? It's very natural mathematically. It's very convenient. When you're actually computing something from a parameterization, this is your only real option. I mean, you could write it like this, but you're going to need to rewrite it like that, right? So I cannot advise that you pick one and only one, right? You should use the right notation for the right, for the particulars of your context. And then, and again, sadly, you just have to heads up about the orientation worry when you switch from one of these, where everything is intrinsic to the given surface, to this down here, where the way it's written is intrinsic to the parameterization. You just have to be heads up. Yeah, sadly. There's no notational workaround on this. Good question, though. Anybody else? Everybody with me? Okay, let me show you an example. So now this is going to look like the same example we did previously, and it's very, very, very similar. It is the same vector fields, the same portion of the same surface with the same equation above the same unit square. The only thing that's different in this example is it says right here, oriented downward, right? We want to compute the downward flux. That's language indicating that I should think of my surface as oriented downward. Okay. All right. How am I going to deal with the fact that I need it to be oriented downward? Where do I plug that into the calculation? Good news. You don't. For the first couple of seconds of the computation, for the first few steps, you kind of ignore the orientation. Okay, and so you write down your parameterization. Whatever, take a pick, whatever's convenient. No worries. You take the appropriate partials. You do the cross product, right, to get your capital N, and then you set your pen down and pause, right? This is very, very important. You cannot just keep plugging and chugging. You're going to want to, right? You're going to see that capital N. You're going to want to plug that in and compute. You can't. This is where you have to think carefully about the orientation. You've been told in the statement of the question that downward is the positive. You parameterize in such a way as to result in this as your parameterization normal. And now we have to ask the question, did we get it right or did we get it wrong? And check it out. My normal vector here pretty clearly has a positive third coordinate. That means that this normal vector is pointing somewhat upward. Not exactly, right? These other coordinates aren't zeros. It's not exactly upward, but there is no reasonable sense in which you could view this orientation as being downward. But it was supposed to be downward. So I parameterized wrong. Does everybody see that? Well, do I need to reparameterize and do the whole thing over so that I parameterized right? Thankfully, no. You do not have to reparameterize. You can just recognize that you're doing it backwards and that you know, therefore, that your answer is going to be off by a minus sign. And so you just recognize the problem. Acknowledge that you parameterized backwards, and then fix it by inserting a minus sign and the appropriate place in the calculation. That's all you got to do. Right? Just, identify when you're off by -1 and then fix it. Everything else is just plug and chug, just like we did in the last question. Is that cool? Everybody all right? Now, there is an important detail here. A lot of students get this wrong. Remember, it's not about the answer, it's about the argument. Right? A right answer with an invalid argument is an invalid argument, and the argument is what's being graded. So, again, I can't emphasize that enough. Y'all have heard me say it a million times, and probably hear it a few thousand more times. So, specifically here, the important point is that you have to get it right as to where you fix it with the minus sign, right? So let me document which of the things that I have written down here come from, are intrinsic to the surface, and which are results of the parameterization. And starting with, let's see here. I guess I can do this let me do green. So the flux that we've been asked for, that's asking for a flux through a oriented surface. That means intrinsic to the surface. This notation right here, right, that ds vector, this includes the unit normal in the direction of the surface's intrinsic orientation. So that is intrinsic to the surface. But this thing down here comes from the parameterization. This capital N comes from the parameterization. So this is where the switch happens, and therefore this is where the minus sign goes, and of course it's got to carry over after that. Don't just drop it, right? But where it's inserted, where the minus sign is first inserted, needs to be there. Now let's entertain what would be wrong if you put it in the wrong place. Let's see here. So just to get my color coding right. So the green is from the surface, the purple is from the parameterization. If you put your minus sign there only, now you're saying that these two things are negatives of each other, and they're not. These two things are the same. The two things in purple are the same. So that would be an incorrect bit of reasoning. Right? So let's see here. I'm running out of good colors. So you would, that equation right there would be wrong. But then also, you'd be saying these two things are the same, which they are not. And that means that this equation here would be wrong too. Right? So you see why it matters, right? I mean, you have to get the minus sign in the in the right place, because you want everything, all of your statements, all of your equations to be actually true statements. Right? That's what we do in math, right? So it's a dangerous little, delicate little business. It's an important distinction to be careful about, and just heads up on that. Okay, now let's talk about the language. How do you describe these orientations? This is unavoidably sloppy language. There's no way around it that I'm aware of. Right? And here's the reason why. If you're looking at, let's say, this paraboloid right there, for example, well, there are two orientations, one of which is like this that I have highlighted in green there. The other orientation option being what I have highlighted in blue right there. And how are you going to distinguish the green from the blue? I think describing them as upward versus downward is a great option. Because if you look at these green vectors, they're mostly not pointing exactly up. But these green vectors, none of them is in any sense downward. Not even a little bit. And you look at these blue vectors, they're not all pointing straight down, but none of them is in any sense upward. Right? So these terms, upward and downward, they're not exactly descriptive, but they do 100% remove any ambiguity. You know there's two options on how you can orient a surface. This is an entirely unambiguous choice of language here. Does that make sense? So perfection's not the goal. If you wanted to give a truly perfect description of, let's say, this green orientation right here, well, you'd have to write down equations. I mean, it's too complicated. They point in different directions everywhere. And sometimes in casual parlance, I don't want to have to be, I just want to remove the ambiguity. There's two options. I want to communicate effectively which option of the two I'm talking about. So this kind of language, again, a little sloppy. It's not exactly precise, but it is entirely unambiguous. That's our goal here. So, so now there's other options, inward versus outward. I don't think anyone would misunderstand if you were to say inward versus outward. I will point out that technically there isn't a closed surface here. Technically there isn't an inside. Right? So it's a little cringy, but it's not the worst thing in the world, and that's, I'm going to say basically fine, but all else being equal, upward versus downward I think is better. Right? And then further realize your best choices of language, your options for language, depend very much on the kind of surface you're talking about. So for example, on this sphere, you look at these two options for your orientations. I think I missed one there. You look at these two options for your two possible orientations on that sphere. And let's entertain the question of upward versus downward. And well, here's the problem. Some of those green vectors are upward, some are downward. Some of those blue vectors are upward, some are downward. I don't know what you mean if you say upward. Right? It could be referring to the fact that some of the green vectors are upward. You could be referring to the fact that some of the blue vectors are upward. It's ambiguous. It doesn't remove the lack of clarity. So you can't use that language. But in this case, you'll notice, of course, inward versus outward, perfectly fine. There definitely is an inside. There definitely is an outside. That's a great choice there. Everybody on board? All right. Okay. For this surface, it's a little bit weird. I like the idea of this right here, oriented in the positive y direction. Again, you can no one would guess by this language right here, positive y direction, no one would guess this orientation where all of the y coordinates are negative. So entirely unambiguous. All right. Okay. Yeah. So every so often you get lucky. You got to cash those in, right? Don't go to tons and tons of trouble when you don't have to. It's very nice on, surprisingly often. Again, the world is full of symmetries. The world is full of good luck to be had. So cash in on those when you can. Here's an example. We have this sphere. It says here oriented outward. So our normal vector is outward because it says so. Not because you have to. Not because a sphere is intrinsically outward. It's not. Right? Because it says so. All right, that's where that orientation comes from. So that being the case, y'all remember we made an argument very much like this when we were talking about vector line integrals. This outward oriented unit normal is pretty clearly parallel to the position vector. Spheres are awesome in that way, right? This claim here that these are parallel is a peculiarity of spheres centered at the origin, right? And it's really nice in this case in particular because that means you can write down an easy formula for your capital N. And of course you are given your vector field is that, and then I haven't parameterized anything. I haven't taken any partial derivatives, cross products, argued about, I don't even technically need to know the orientation on this one. I can just immediately see that this dot product is 0 and therefore the integral is 0 and we're done and no tedious, no massive sines and cosines and phis and thetas and all that ugliness. Nope, not in this one. Yep.
This is a closed surface?
Yes.
And is that why it's also 0?
No. There's plenty of situations where there are plenty of vector fields where the flux through a closed surface can be non-zero.
Okay.
Absolutely, yeah.
So what's the condition where the closed surface indicates that something is 0? I remember there was something.
Yeah, we're going to get to that later. There's a special case. We're going to need to talk about Gauss's divergence theorem first. So that will come up, and that's a thing, but it's not general, right? That's a special case.
Is that circulation? Like circulation through a closed surface? 0?
No, there's.
We've talked about it in the past.
We've talked about circulation of gradient vectors around closed curves.
Okay.
Yeah, that's probably what you're thinking of.
And that was 0.
Again, but in the special case where you're talking about gradients, those special vector fields. So again, it's a special property.
Yeah. Okay.
Yeah. Right. Yeah. Okay. Okay. Next thing. Next little bit of good fortune. This kind of thing again. This is not rare. Right? I scored on this trick many times in my college days. And here's the idea. So you've got this plane right here. And you're looking specifically at the part of it that satisfies some scary-looking inequality, and specifically it's, this chunk right there in dark green. Oh, my gosh. Oriented in a certain way, fine. Oriented, like that. So we have these normal vectors, okay. And I want to compute a flux. And I have a scary vector field. So again, look, I suppose you could, plug and chug on this, and it wouldn't, it's doable, I suppose. But I think much more easy, right? And we should all be in the market for easy, is to notice very conveniently that our entire surface here, because our entire surface, every point in the integral that we're interested in other words, is on this plane. and therefore satisfies this equation. Right? And therefore, this is 0. Right? That means that our second coordinate of our vector field is 0 for our entire surface. For the whole calculation that we're interested in. Now, it's not 0 over here, and it's not 0 over there, and I don't care. We're never going to go over there. Right? All we care about on our surface in question, y is 3, and therefore this second coordinate is 0. Now, the next key observation, and again, capitalizing on some geometric good fortune, because this is a flat plane, I know that the normal vector is easy to write down. Now, that's not because y is 3 specifically. This is because y is just a constant. Any constant, right, would give me this result. And so my normal vector, being 0, 1, 0, now, having documented all of our sort of geometric lucky breaks, the question that would have been an ugly vector field to deal with, now we just immediately see, oh yeah, dot product 0. Boom, score, right? Done. Answer 0. We walk away. Does that make sense? Okay. So heads up for this kind of thing. I mean, this you get lucky surprisingly often in at least in my experience. Okay. Now, y'all remember all that business about coordinate line integrals? The punchline with coordinate line integrals was that you can give a justification for how to write down your dx vector in that case. We're going to see an analogous observation here about the ds vector. But the point is your differential, your vector differential, you could write in coordinates. And that allowed for a new notation that, tragically, we have to deal with because it's out there for good reasons, and yes, there's benefits that we will never experience. But nevertheless, even if you don't experience the benefits of that notation, you will experience that notation. And so here we are again, and roughly speaking, the same thing's going to happen. So here's our standing formula for the ds vector. N is that cross product, which I can write out in coordinates, right? Which I can crank out the cross product of. And again, as previously noted some time ago, we observed that seemingly coincidentally, these turn out to be determinants. Right? These are two-dimensional change of variable stretching factors, which is really surprising. It doesn't seem like that should come up when you're talking about a surface in 3 space. Where is the 2 dimensions? Right? So it's a little bit weird. But having written that all down, now, what would we make of this right here? Which you can see right here, I've distributed the ds dt. What would we make of these expressions? And one coordinate at a time, I think you can make some pretty persuasive cases. So for example, this right here, you remember when we saw this kind of thing back in chapter 5, and this became dy dz. So this is a very natural choice of how to write that thing. And then likewise, it's pretty natural to call this dz dx, and it is pretty natural to call this dx dy. So common choice of notation. And with that in mind, noting that ds can be rewritten like so, and noting that our vector field is going to have coordinates like so, you can just write down this dot product, and that dot product becomes all of that. It's just notation. As far as we're interested in this course, this is just notation. So we have just an alternative way to write down a vector surface integral, and some people like this. Some people like to use this even when There's no particular reason to, at least in my experience. Now, which do you like better? It's personal preference. I find this to be a lot to write down. I find that I have to always kind of scratch my head and remind myself, wait a minute, which one of these things is which coordinate of the ds vector, and therefore which one pairs up with which coordinate. It's just a little confusing, and I have to kind of think it through. I can do it, right? But all else being equal, it's a little confusing. It's very clunky. And so given my choice, without better reasons to the contrary, I'll use the compact, convenient, physically natural option. Right? Well, of course I will. That said, this notation, very closely connected to differential forms, which are extremely powerful and very mathematically natural and a really good thing. Amazing results have come out of understanding and studying differential forms. Very big deal, very useful. But we're not going to do any of that stuff. And so the only reason we're talking about this, aside from the cultural point, and I do believe it's, this liberal arts education and all that, right? I think the cultural points are worth talking about. But in practice, where y'all are going to need to know this is that you're going to see these integrals. They are in common use in many contexts. And so when you see this, just remember that's just code for this. Is that cool? Very analogous story to what we saw with coordinate line integrals. Okay. Real quick, I have to point out this one thing. A lot of people look at what I've written here, this dz/dx, and have this natural organizational instinct to put that in alphabetical order and write it as dx/dz. You may experience that urge. You can't do it. Keep in mind that this is just a rewrite of this thing right here, and the z coming before the x is an indication that this z comes before that x, which is an indication of which order to put those rows in the resulting Jacobian matrix. And if you switch the rows, you get a minus sign, right? So dz/dx is not the same as dx/dz in this context. It's super annoying, right? You just got to keep in mind, this is a shorthand notation for a determinant. Determinants, the order matters. So, uncomfortable though it seems, got to leave that as dz/dx. Okay. All right. Okay. Symmetry theorems. By the way, I don't know if you noticed this, but the order that I'm going through these sort of connected ideas, related to vector surface integrals, is exactly the same order that I was going through connected ideas to vector line integrals. And that's on purpose, right? Come back to that point in a minute. Okay. You could probably guess what this is going to say without even reading it, just looking at the layout on the page, right? This theorem, these two NBs that follow it, right, looks exactly like every other symmetry theorem we've seen in this course. And specifically, if your integrand is odd and if your domain is symmetric, I emphasize that means that I'm talking about both of those conditions happening, and specifically that you're using the same plane for both. Then wonderful punchline, your integral is 0 and you don't have to compute anything. Right? Really, really nice fact. Very handy. Big fan. The worry on this, the problem, the bad news, is that this only applies to scalar surface integrals. Only scalar surface integrals. By the way, again, flashbacks, right, to when we were talking about symmetries for line integrals. It was only scalar line integrals. Likewise, only scalar surface integrals. If you have a vector surface integral, The problem is in these normal vectors. And you can see even if you have a perfectly symmetric surface, symmetric through a plane, and imagine every other bit of good fortune you could possibly imagine in the statement of the question, it remains that these two vectors, they're not the same. They're not negatives of each other. They're just not going to be able to make an odd symmetry theorem work. It just doesn't work. So, super dangerous, right? Please, please, please do not look at a vector surface integral and start asking questions about whether the vector field is odd. It doesn't go anywhere. There is no theorem to use, right? There is no odd symmetry theorem. It does not work. Everybody on board with that? So, yeah.
But like looking through the normal vectors there, I would say that the y components of them would cancel out.
Yeah, well, that's just not good enough, right? I mean, you're right that there is a connection, right? So these normal vectors that I have drawn here, they're not the same, they're not negatives, but they are mirror images of each other. And so there is a symmetry theorem that I could write down, but it's not odd symmetry, and it's not even symmetry. It's, oh gosh, and I have to think through every time because the theorem that would work involves the vector field. I can't remember if it's either mirror symmetry or mirror anti-symmetry, and one applies to line integrals and one applies to surface integrals, and it's very confusing. And you got to think through all those details, and you're on the right track toward figuring out one of those theorems. But my strong experience on this is that it's more trouble than it's worth. And so that's why I'm consciously choosing not to show you that theorem. Is that satisfying?
Yeah.
Okay. Anybody else? Okay. All right. Cool. All right. So, yeah. I pointed out a second ago that the ideas that we just, sort of the connected ideas of geometric good fortune and symmetries and stuff like that we've talked about, like the coordinate integrals, all the connected ideas that we talked about for vector line integrals also apply to vector surface integrals. And so we should be suspicious about that. Why is it that these two geometrically different things seem to be already showing some analogies to each other, right? Well, here's where we're going to see the analogies getting a lot stronger. And just as a little bit of context, where does this all come from, and why are we seeing what we're about to see here? It's because these two kinds of integrals, line integrals and surface integrals, specifically vector line integrals and surface integrals, are both examples of integrals of differential forms. And again, there's this mysterious construction that I'm not going to go into in this course because I think it's too much. But again, you don't have to know all the details of how two things connect to notice that they connect, and to therefore be on the lookout for and to be aware of all of the resulting analogous properties and analogous features and et cetera, et cetera. So that's what I want to show you here. I'm not going to show you differential forms, but there is a bunch of neat consequences of the fact that these things are all related to each other. So here we go. And let's see here. I guess I'll do it like this to start. Let's do it like that. Okay, so this is how we do a parametric curve. By the way, you'll notice I've got my parameterization kind of tilted downward. That's just for layout on the page purposes. I just didn't have enough page to stretch it out sideways like we normally would. Apologies for that. So there's a curve parameterization. Here's a surface parameterization. Okay. What's our foot in the door for, what's the first thing we do with a parameterization of a curve? Well, we talk about a derivative. what's the first thing we do with a surface parameterization? Well, we take various partial derivatives, and from which we get our capital N vector. So capital N is not itself exactly a derivative, but it comes from derivatives, so I'm going to code those as being analogous. And so there's an analogy of sorts in the fact that both cases we're taking derivatives of our parameterization, but notice further there is an analogy between how those vectors show up in the resulting algebra. Now, all the algebra I have written down here is old news. There's nothing new down here in this algebra. That's all rehash. But notice that they show up in analogous ways in that existing algebra. So likewise, we can talk about the unit tangent vector, and we can talk about the unit normal vector. Both of these are just unitized versions, right, of the existing green vectors. Both of them describe the orientations. Now, geometrically different. Unit tangent vector tells you about how which is the correct direction along the curve. The unit normal tells you what is the correct direction through the surface. Geometrically different, but both of them are telling you the orientation relevant to that geometric object. And again, both of them show up analogously in the algebra. Okay, continuing. There's the ds scalar telling you how big that piece of curve is. There's the ds scalar here telling you how big that piece of surface is. Both showing up analogously in the algebra. All right? I mean, the analogies just keep coming. Here's the next one. Let's talk about the dx vector versus the ds vector. Both have magnitudes telling you the size. Both have directions telling you the orientation. And both show up analogously in the algebra. So that's, I think, pretty persuasive that there's a lot going on underneath the surface that we're not seeing, right? I mean, what are the odds that this kind of level of coincidence would just happen randomly? It's not. It is absolutely not random. All of this is happening because ultimately both of these kinds of integrals are really special cases of the same construction. They're special cases of integrals of differential forms. So let's see here. Just for color persuasion, I'm going to go back into here and highlight further down all the ways that these continue to be analogous. Okay, let's see here. The orange. So let's see here. And then let's see our ds and dx vectors, like so. So just bonkers analogous. So I hope you'll find that eyebrow raising. Again, I have two goals here. One is cultural, right? It's good to know that there are bigger ideas afoot, even if we don't necessarily see those, right? But also I think there's a really good learning tool here. And because you know that there are these strong analogies, don't worry about why, but the mere fact of knowing that there are these very strong analogies will help you understand, will help you retain these relationships, right? So if you have let's suppose you have a comfortable understanding of all this stuff with vector line integrals, but you're a little kind of shaky on the business with all the surface integrals, everything that you understand over here, you can say, all right, well, I just need to know what's the surface analog of what I understand over here, and that will give you what should be over here. Right, so again, this is not two separate large sets of equations to know. This is two examples of one pattern of equations to know. And I think that's pedagogically really useful. So there's that. Okay, how are we doing? Questions? This isn't in the book, by the way. I think this is a good little add-on. I hope you'll find useful. Okay. All right. Moving along. 7.3. This is another one of these sections that I don't really know how to explain this, but Kali made some weird decisions about which sections, should be their own sections. And there's stuff like 5.4, I think it is, that's like teeny tiny. There's just like one idea. Hardly anything happens. And then there's 5.5, which is this great big massive thing that took us more than 3 lectures to make it through. Right? So same thing here. 7.3 is massive. There's a ton of stuff to say about Gauss's divergence theorem. I really think that would still be a large section even if it were on its own. And there's likewise a ton of stuff to say about Stokes' curl theorem. So this is another one of these massive sections that we're not going to get through this in one lecture or two. Or I don't remember the exact numbers, but I'd be pretty surprised if we get through it in 3. It's a big section. So anyway, here we go. I'm going to start by talking about Gauss's theorem. Kali starts with Stokes. I think it's at a minimum, that's very non-standard. Most books start with Gauss. This is has a lot of features in common with Green's theorem. Right? So you remember with Green's theorem was our first example of what I like to call an accumulation theorem. So we identified what we mean by boundary orientations. We're going to have a new convention, arbitrary but standard, convention on what the word boundary means in this context. We're going to identify an accumulating quantity. We're going to make the case that accumulating quantities behave like stuff. Right? They aren't physically stuff, but they behave like stuff, and so you can pretend that it's stuff, and everything works out. And then we're going to talk about an associated density, right? Is this all ringing bells, I hope, right? If you go back through how we developed Green's theorem, it's the exact same sort of outline. And there will be then a resulting theorem. So very, very strong analogy. I think it's really useful to, when you're reviewing these ideas, do the kind of the back and forth thing. Look at the analogous steps for Green's theorem, the analogous steps for what we're doing now with Gauss's theorem, and do like this and compare and contrast. And of course, it's geometrically different. There will be resulting, differences in how the algebra works out and how the equations lay on the page. Of course. But the analogies are very, very strong. Okay, so here we go. What do we mean by the word boundary? Okay, so if you have a solid such as what I have highlighted in gray here, I'm extra highlighting in green. If you have a solid, now notice this is a weird solid. It's a solid with an air bubble inside of it. Right? Nevertheless, it's a solid of sorts. It's three-dimensional. It has this green region has a volume. Right? Okay, well, what do we mean by the word boundary? And here's the rule. Boundary is now an oriented thing. Oriented now means at a point on the boundary. Keeping in mind that the boundary is the sort of the border between solid and not solid. The orientation is always away from the solid and into the not solid. That's the rule. So, for example, at this point, it's like that. At this point here, it's like that. Notice again, away from where the solid is and into where the not solid is. Okay. Now, a lot of people misstate this. And with this example in mind, a lot of people say, okay, oriented outward. Not always. Right? So now, Here's another example of the analogy. Remember, we had this exact same thing come up with Green's theorem when we were developing the idea of boundaries, and a lot of people like to just say counterclockwise. But again, it's not always. Same story here. Okay. Everybody on board? I confess, totally arbitrary. Why away? Why couldn't we have said toward? Valid. We could have. But we didn't. And we have 100 and some odd, probably 150, probably more. I forget the history, but call it 150 years of established precedent, and we have to get on board with that precedent. And the precedent, arbitrary though it is away from the solid. And it looks like I'm out of time now, so we will draw the line right there. We will pick up here on Friday. See y'all later. Have a good one. And don't forget about attendance.